NASA's James Webb Space Telescope is a true technological marvel. The largest and most complex space telescope ever built, Webb will be able to gather light that has been traveling for 13.5 billion years, almost since the beginning of the universe. In effect, Webb is a time machine, allowing us to peer at the first galaxies to form after the Big Bang. Because it gathers infrared light, it will see right through the giant clouds of dust that block the view of most other telescopes. The Webb telescope is at least 100 times more powerful than the Hubble Space Telescope, and with its golden mirror, astronomers are hoping to catch glimpses of the universe like never before. The universe, time and space all began about 13.8 billion years ago with the Big Bang. For the first few 100,000 years, the universe was a hot, dense fluid of protons, electrons and neutrons, the tiny particles that make up atoms. As the universe cooled, protons and neutrons combined into ionized hydrogen and helium, which had a positive charge, and eventually attracted all those negatively charged electrons. This process, known as recombination, occurred about 240,000 to 300,000 years after the Big Bang. Light that previously couldn't travel without being scattered by the dense ionized plasma of early particles could now travel freely. The very first form of light we can look back and see comes from this time and is known as the cosmic microwave background radiation. It is essentially a map of temperature fluctuations across the universe left behind from the Big Bang. The fluctuations give clues about the origin of galaxies and the large-scale structure of galaxies. There were still no stars in the universe at this time, so the next several hundred million years are known as the cosmic dark ages. Current theory predicts that the earliest stars were big 30 to 300 times the size of our Sun and burned quickly, ending in supernova explosions after just a few million years. Observing these luminous supernova is one of the few ways scientists could study the earliest stars. This is vital to understanding the formation of objects such as the first galaxies. Studying these early objects will help to fill in some gaps in our knowledge. How did early stars and galaxies take shape? How do black holes figure into the formation of the early universe? What about the cosmic material that is undetectable, known as dark matter? Is there evidence for it in the early eons of the universe? These are some of the perplexing and fascinating questions that astronomers can begin unraveling with Webb telescope. But how is Webb able to see back in time? Because light takes time to travel through a space, there is a delay between when we see something and when it actually happened. In the small space of a room, the time for light to travel from the bulb to the corner is not noticeable. Between the Earth and the Moon, light takes 1.3 seconds, which means that we see the Moon as it was 1.3 seconds ago. Multiplied over the vast distances of the universe, light can take many years to reach us. The rainbow of light that the human eye can see is a small portion of the total range of light known in science as the electromagnetic spectrum. Telescopes can be engineered to detect lights outside the visual range to show us otherwise hidden regions of space. The James Webb Space Telescope detects near-infrared and mid-infrared wavelengths, the light beyond the red end of the visual spectrum. Infrared light is important to astronomy in three major ways. First, some objects are just better observed in infrared wavelengths. Some bodies of matter that are cold and do not emit much energy or visual brightness, like people or young planet, still radiate in the infrared. Humans perceive this as a heat, while some other animals, like snakes, are able to see infrared energy. Visual light's short, tight wavelengths are prone to bouncing off dust particles, making it hard for visual light to escape from a dense nebula or protoplanetary cloud of gas and dust. The longer wavelengths of infrared light slip past dust more easily, and therefore instruments that detect infrared light, like those on Webb telescope, are able to see the objects that emitted that light inside a dusty cloud. In this way, Webb will reveal a hidden universe of stars and planet formation that is literally not visual. Finally, infrared light holds clues to many mysteries from the beginning of everything, the first stars and galaxies in the early universe after the Big Bang. Through a process called cosmological redshifting, light is stretched as the universe expands. So light from stars that is emitted in shorter ultraviolet and visual wavelengths is stretched to the longer wavelengths of infrared light. The Webb telescope was specifically designed to observe this light, which comes from some of oldest galaxies to take form. The most important part of Webb's design is its giant primary mirror. Telescopes work by using their mirrors to collect more light than the human eye can detect on its own. The more light a telescope mirror collects, the sharper the image and the deeper into a space the telescope can see. A large mirror is even more important for infrared telescopes. The clarity of a telescope images or resolution is determined by the size of the mirror compared to the wavelength of light. Since infrared is a longer wavelength, a large mirror is needed to produce a quality image. Webb's primary mirror is made up of 18 hexagonal segments that together measure over 21 feet or 6.6 meters across. The segments are six-sided because that configuration allows the segments to come closest to forming a circle, the best shape for a telescope mirror. The mirror folded inside the rocket opens after the telescope deploys. At first, the segments look at different points in the sky. On the ground, Webb's operators follow a painstaking process of aligning the segments so they all focus on the same point. Once the operators are done, the segments operate as a single unified mirror. Webb's actual scientific observations are performed by 4 instruments, each especially designed to study different aspects of infrared light, and each instrument has unique features that allow astronomers to study a variety of astronomical objects in different ways. These instruments include new technologies like the microshutter array that were developed for Webb to increase the telescope's scientific capability and efficient operation throughout its mission. Both aspects are essential to Webb's usefulness. Efficiency allows more astronomers to make use of Webb while it's operational, and the best possible science capability will help those astronomers investigate some of our most fundamental questions, like how did we get here, how does the universe work. The James Webb Telescope gathers its scientific data as infrared light. To detect the faint signals of objects billions of light years away, the instruments inside the telescope have to be kept very cold. Otherwise, those infrared signals could get lost in the heat of the telescope. That's why the telescope has a sunshield to protect its instruments and mirrors. The telescope's sunshield is about the size of a tennis court. The temperature difference between the sun-facing and shaded sides of the telescope is more than 600 degrees Fahrenheit. Webb charts new territory in many ways, from its innovative design to its size to its unfolding in space, and finally to the high-resolution infrared light images it will provide over the course of its mission. The successes and discoveries of its mission will influence astronomy for many years to come. With a mirror that towers over 2 stories high and a sprawling sunshield, the Webb telescope is the biggest observatory ever launched into space. The bigger the telescope, specifically its light-gathering mirror, the better its vision. The 6-ton Webb telescope was designed to launch aboard an Ariane 5 rocket, which is just a little smaller than the space shuttle used to launch the Hubble Space Telescope. The James Webb Space Telescope will be the world's premier space science observatory when it launched in December 2021. Webb will solve mysteries in our solar system, look beyond to distant worlds around the other stars, and probe the mysterious structure and origins of our universe and our place in it. It will explore every phase of cosmic history, from within our solar system to the most distant observable galaxy in the early universe and everything in between. Webb will reveal new and unexpected discoveries and help humanity understand the origin of the universe and our place in it.